Okay, welcome back. We're going to continue our discussion of heat and the second law of thermodynamics. This will be our third lesson on this topic. And we're going to essentially continue our discussion of what is meant by entropy. In our previous lesson, we gave you a number of examples of entropy. Entropy being a measure of the disorder of a system. As we talked about the second law of thermodynamics, which states that the entropy or the disorder of an isolated system increases with time. And we gave examples of entropy in terms of the increase in randomness, in terms of things like shuffling of a deck of cards, of our rooms becoming more messy with time. And we talked about the different phases of matter, about how the atoms or the molecules of a gas have a higher level of freedom, of motional freedom or disorder than in a liquid, which have more motional freedom than a solid, because in a solid the atoms or molecules are in fixed lattice positions. A consequence is that at room temperature there will be a tendency for ice to melt into the liquid phase, to increase the entropy of the water molecules. And we talked about the tendency of gas molecules to diffuse between two sides of a compartment, going from the side where there is a higher pressure or a higher number of gas molecules to a lower number, to essentially spread out the gas molecules. And we talked about a statistical explanation for entropy and how the basic concept of entropy can be understood in terms of statistics. Well, how about the flow of thermal energy from a hotter to a colder body, which is where we began this chapter? Yes, we've talked about how we can understand entropy in terms of the movement of molecules from a more concentrated area to a less concentrated area. That is, molecules tend to diffuse and spread out. But how about thermal energy? It turns out we can understand the flow of thermal energy from a hotter body to a colder body in essentially the same way. Let's consider, again, an apparatus with two sides, left and right, in which we have hotter molecules, in red in this drawing, on the left, and colder molecules on the right. And we have, again, a valve which we can open. Now, what will happen when we open this valve? Well, if the molecules are free to diffuse, they will, and the hotter molecules will diffuse to the right, and the colder molecules will diffuse to the left as a function of time. And as you can see at the bottom, we will have a comfortable mixture of the hotter and colder molecules, resulting in an averaged temperature. So the flow of thermal energy from a hotter to a colder body can essentially be understood in the same way as the flow of molecules. Now, it turns out it took a number of years for this type of explanation to be fully developed, because up until about 1800, the notion of an atom was not universally accepted. But once scientists understood that matter was made of smallest particles, atoms or molecules, then the statistical behavior in the movement of molecules was understood. Now, there was an interesting thought problem that was discussed for a number of years, in which scientists wondered, what if there was a small devilish creature, and it actually was called Maxwell's demon, a hypothetical creature, that could sit at this valve and could determine which of the molecules were hot, which were cold? Could, in fact, that demon only allow hot molecules to move in one direction and cold molecules in the other direction? So, for example, if you started with the bottom arrangement with a mixture of hot and cold, red and blue molecules on both sides, could this demon let only the hot molecules go to the left and let only the cold molecules go to the right, resulting in a separation of hot and cold? Now, scientists thought about this and over a period of time developed a number of arguments as to why this could not happen, because in fact, this is not what we observe. We do not observe experimentally that we can have a container of gas or liquid or solid in which spontaneously there will be a separation of hot regions and cold regions. For example, if we fill a glass with water, tap water, it will not spontaneously form ice cubes in front of us with the migration of the warmer molecules into the liquid phase and the colder molecules now then becoming solid ice. That is, the flow of thermal energy from cold to hot does not occur. Instead, it always flows from hot to cold. The statistical approach to understanding matter and understanding the second law was advanced by a number of scientists, but one very noteworthy one was Ludwig Boltzmann. Ludwig Boltzmann was a brilliant but troubled scientist, and he came up with the following equation. Entropy, S, is equal to a constant, K, a constant that is so important that we in fact call it Boltzmann's constant, times the natural log, that's what ln is, times W. Now W, since Boltzmann was German, W stood for Wahrscheinlichkeit, a typical German word with multiple syllables, but essentially it means ways of finding a system or the probability of finding a system in a particular state. Now this single equation is the basis for the statistical explanation of entropy. So important is this equation that you can see that it was placed on the tombstone of Ludwig Boltzmann. Now we've talked about some very heady topics in the last couple of video lessons. So let me summarize. Entropy, S, capital S, is a measure of the disorder of a system. And the entropy of the universe increases with time. This second statement is what is usually referred to as the second law of thermodynamics. Now, creating order, that is, lowering entropy, separating hot from cold, straightening our room, creating order in this way can be done, but only at the expense of performing work. And we'll get into this more in the next lesson. That is, we can freeze water into ice, we can separate hot and cold, we can straighten our room, we can straighten out the deck of cards, but to do so requires the expenditure of energy to do work. Entropy has a statistical basis, Boltzmann's equation. Entropy is equal to K ln of Wahrscheinlichkeit, W. And the statistical explanation applies both to the position and the kinetic energy of particles. Consequently, the second law indicates that energy also disperses or spreads with time. Not only do molecules spread with time, but thermal energy spreads with time. That is, heat flows from hot to cold. Now, the last point made is that the second law in entropy, for it to increase with time, this implies that there is a direction to time. Let me pause and try to explain this. You notice that in some of the videos I showed, we had someone riding a bike backwards, or we had the Dixie cups spontaneously assembling into a pyramid. And of course, it was obvious that we were showing the film backwards at that time because that is not our experience. That is, our experience is that things become disordered with time, not that they become ordered with time. Or another way of considering this is that time marches in only one direction. It marches in a positive direction. Because if time could go in reverse, then some of these things that we saw would not have been surprising to us. But time only marches forward. Now that statement may seem obvious, but it is in some sense profound. We'll pause now, but let me give you a preview. In the next lesson, Dr. Teresa Levitt will give us a historical perspective, and she'll talk about the development of the second law and the concepts of entropy, and no doubt some of the interesting scientists. And then I will come back later with a lesson on the consequences of the second law and entropy in our daily lives. And I'll see you then.